Hello everyone and welcome back. In this video we're going to talk about the chi-square test of homogeneity and the chi-square test for independence. When we want to compare the distribution of a single categorical variable among two or more groups, then we can use the chi-square test of homogeneity. And as the name suggests, this test will ask whether the distribution of a categorical variable is the same among different groups. And this test is different from the goodness of fit test since there is no model to compare to. And this test is also a generalization of the two proportion Z test to multiple categories or multiple groups. Now the homogeneity test comes with a built-in null hypothesis. We assume that the distribution of our categorical variable is the same among all groups. The assumptions and conditions are the same as the goodness of fit test, with a slight exception on how we calculate the expected counts and the degrees of freedom. Now to find the expected counts for each cell in a contingency table, we multiply the row total with the column total, and then divide this by the grand total. And to find the degrees of freedom, we take the number of rows minus 1 and multiply it by the number of columns minus 1. So let's take a look at an example. Suppose we have three different income brackets: the low income group that makes less than 50,000, the medium income group which makes between 50,000 and 100,000, and the high income group which makes over 100,000. Now assume that we have a random sample of 250 households from California and another sample of 150 households from Wisconsin. So the distribution of income groups in each of these states are given in the table. Now let's use an appropriate test to test whether the distribution of income is the same for California and Wisconsin at the 2.5% significance level. So here we want to use a test of homogeneity because we want to see whether the distribution of income is the same among two different populations. So let's first find the expected counts. So to find the expected counts for the low income group in California, we look at the row total, which is 104, and the column total, which is 250. So we multiply both of these values, and then we divide this by the grand total, which is 400. And this works out to be 65. Now to find the expected counts for the low income group in Wisconsin, again we look at the row total, which is 104, and the column total, which is 150. So we multiply these together and then divide by the grand total of 400. And this gives us an expected count of 39. And then for the medium income group in California, we take 120 multiplied by 250 over 400, and this gives us 75. And for the medium income group in Wisconsin, we have 120 times 150 over 400, which gives us 45. And then the high income group in California, we take 176 multiplied by 250 and divide by 400, which gives us 110. And then the high income group in Wisconsin, we have 176 times 150 over 400. And this is 66. So now let's write the hypotheses for our test. So the null hypothesis for the test of homogeneity is to assume that the distribution of income groups in California is the same as Wisconsin. And the alternative is that at least one of the proportions of income groups differs between the states. So now let's check the assumptions and conditions. So we have the independence assumption. So within and across each state, a household that belongs to an income group should not affect other households that belong to other income groups. So we check the randomization condition. So we're given that we have random samples of households from both states. So the randomization condition is met. And lastly, we check the sample size. So we need a large enough sample. And we check the expected cell frequency condition. We observe that all expected counts are at least 5. And so the expected cell frequency condition is met. And we also have the counted data condition. And so all of the values in our table are in counts. And so this condition is met. So now we can calculate our test statistic. So we take the sum of the squared difference from the observed and expected and divide it by the expected. So for the low income group in California, we observed 70 and we expect 65. So we take 70 minus 65 squared and divide it by the expected, which is 65. And for the low income group in Wisconsin, we observed 34. We expect 39. So we have 34 minus 39 squared over 39. And we do the same calculations for the other income groups. So that means we have 80 minus 75 squared over 75 for the medium income group in California. And then the medium income group in Wisconsin, we have 40 observed. We expect 45. And then for the high income group in California, we have 100 observed. And we expect 110. And then the high income group in Wisconsin, we have 76 observed, and we expect 66. And so if you perform this calculation, we get a chi-squared statistic of 4.339, rounding to 3 decimal places. Next, we need to determine the degrees of freedom for our sampling distribution model. And for the chi-squared test of homogeneity, we take the number of rows, subtract 1, multiply by the number of columns, subtract 1. So if we look in our contingency table, we have 3 rows and 2 columns. So that means our degrees of freedom will be 3 minus 1 times 2 minus 1, which becomes 2 times 1, which is 2. So that means our p-value will be the area to the right of 4.339 with 2 degrees of freedom. So using our table, we will look up 2 degrees of freedom and we'll find where 4.339 falls within that row. So notice that 4.339 falls to the left of the table, and the closest value is 4.605. So let's write down what the table gives us for the area. So the table tells us that the area to the right of 4.605 is equal to 0.1. So the area to the right of 4.605 is 0.1. And our test statistic is 4.339. So we want the area to the right of this value. Well, since the area to the right of 4.605 is equal to 0.1, this tells us that our p-value is going to be larger than 0.1. So using an interval, we can say that the p-value will be between 0.1 and 1. So now let's compare the p-value to the significance level. Our significance level is 0.025. And our p-value is a value larger than 0.1. So since our p-value is larger than the significance level of 0.025, we will fail to reject the null hypothesis. So this tells us that there is insufficient evidence to conclude that at least one of the proportions of income groups is different between the states. Now we'll look at the third chi-square test. If we have two categorical variables that are measured from the same population, then we can see whether they are independent by using a chi-squared test for independence. Now this test will determine whether there is an association between two categorical variables. Now the calculations for the test for independence are identical to the test of homogeneity. Now the only difference is that the test for independence has two categorical variables that is measured from a single population, whereas the test of homogeneity has a single categorical variable that is measured from two or more populations. So let's take a look at an example. Suppose a survey was conducted to evaluate the effectiveness of a new flu vaccine. The vaccination consists of a 2-shot sequence over 2 weeks, and a random sample of 1,000 residents were selected in the following spring, and we have the following data. So is there evidence that the number of flu shots and the incidence of the flu are independent? So let's perform a test of hypothesis at the 1% significance level. So let's first find the expected counts. So for the no vaccine and the flu category, there is a row total of 46 and a column total of 313. So the expected counts will be 46 times 313 divided by the grand total, which is 1,000. And this comes out to 14.398. And I'll leave it as an exercise for you to check the other expected counts. So for the 1-shot and the flu category, we have an expected count of 5.014. For the 2-shot and flu group, we have 26.588. The no vaccine and the no flu group has an expected count of 298.602. Then 103.986 for the 1-shot and no flu group. And lastly, we have 551.412 for the 2-shot and no vaccine group. So now let's write down the hypotheses for the test. So the null hypothesis for the test of independence is to assume that the two categorical variables are independent. So in this case, the number of flu shots and the incidence of the flu are independent. And the alternative is that the two variables are not independent. So the number of flu shots and the incidence of the flu are not independent. So now let's check the assumptions and conditions. So we have the counted data condition. So the data that we have are in counts. So this condition is satisfied. We have independence. So residents that are receiving or not receiving flu shots and the incidence of the flu should not affect other residents receiving the flu shots or their incidence of the flu. So we'll check the randomization condition. So what we have is 1,000 residents that were randomly chosen. So we have a random sample. So that condition is met. And we also have the expected cell frequency. And all expected counts are at least 5. And so this condition is met. So now we can calculate our test statistic. So we'll take the observed minus expected squared and divide it by the expected, and then add all of these values for each of the cells. So for the no vaccine and the flu group, we have an observed count of 24. We expect 14.398. So we divide this by 14.398. Then we add this to the one shot and the flu group. So we have 9 observed. We expect 5.014. Then we add this to the 2 shot and the flu group. We observed 13. We expect 26.588. And then we add this to the no vaccine and the no flu group. We observe 289. We expect 298.602. Then we add this to the one shot and the no flu group. We observe 100. We expect 103.986. And lastly, we have the 2 shot and no vaccine, which is 565 observed, and we expect 551.14 or 412 squared over the expected. And if you perform the calculation, we get 17.313, rounding to 3 decimals. So now we'll calculate the degrees of freedom. We'll take the number of rows, minus 1, times the number of columns, minus 1. So looking at our table, there are 2 rows and 3 columns. So that's 2 minus 1 times 3 minus 1, which is 1 times 2, which is 2. So now that we have our test statistic, we can find the p-value, which is the area to the right of 17.313 with 2 degrees of freedom. So for 2 degrees of freedom, we'll locate where 17.313 falls within the table. And if you look in our table, 17.313 falls to the right of the table. So the closest value is 13.816. So let's write down what the table is giving us for the area. So the table tells us that the area to the right of 13.816 is equal to 0.001. Okay, so the area to the right of 13.816 is 0.001. And so for our test statistic, we have 17.313, which corresponds to this red region. So since the area to the right of 13.816 is equal to 0.001, that tells us our p-value, which is the area to the right of 17.313, will be smaller than 0.001. So we can write this in an interval. So the p-value will be a number between 0 and 0.01. So now we'll compare our p-value to the significance level of 0.01. So the p-value is a number that's smaller than 0.001. So it will be smaller than the significance level of 0.01. So that means we reject the null hypothesis. And remember, the null hypothesis for the test for independence is that the two categorical variables are independent. So that tells us that there is sufficient evidence to conclude that the incidence of the flu is impacted by the number of flu shots. So there is some association between our two variables. And so that concludes our lesson for this video. In the next video, we will start looking at inferences for numerical data, and I'll see you then.